Dear students, in this video we are going to discuss hydrogen atom wave functions. As from the solution of the Schrodinger wave equation we get the energy and wave function. As the wave functions here means the orbital, so we can from the orbitals we can find that where the electron is around the nucleus, we can find we can define the area around which we can localize the electron, around which we can find the electron around the nucleus. So in this video we are going to discuss all about the wave function, about the orbitals and the shape of the orbitals. And so first we need to know about the wave functions or orbital for the hydrogen atom. So solving the Schrodinger wave equation provides the values for the energy and wave function, which depends on the r, theta and phi. So it means that in order to know about the wave functions, first we need to know about the radius and angles theta and phi. So all of the three quantum numbers are needed to describe the wave function in 3 dimensions. So it means that if we want to know about the wave function, we must know about the three quantum numbers. So the first quantum number is the principal quantum number n, and it determines the binding energy, that is the energy levels are shells. That is the principal quantum number determines the energy of the energy levels or energy shells. It tells us it's all about the energy of different energy levels. Is called as the principal quantum number, or in other words is also gives us the information about the quantization of energy of different shells. And second quantum number can be represented by the L, and it is called as angular momentum quantum number. So L is related to the N, and it determines the angular momentum, and it describes the shape of the orbital. Largest value of L can be equal to the n minus 1. So its values depends on value of this principal quantum number, and as I have already told you that, and tells us about the quantization of energy. In the same way, L which is equal to the angular momentum quantum number, which is also called as the orbital quantum number. It tells us about the quantization of angular momentum, and it describes different subshells within the shell, within the principal shells. So another quantum number which can be represented by m, it is called as the magnetic quantum number. So magnetic quantum number, it is related to the L, that is orbital quantum number or angular momentum quantum number, and it determines the behavior of the atom within the magnetic field. It describes the specific orbitals. It tells us about the specific orbitals, that is, in other words, we can say that when we place the atom within the magnetic field, it tells us about the orientation of the angular momentum directions, as and define the principal shells or energy levels. L describes the different subshells or orbitals within the principal shells, and magnetic quantum number, in other way, it describes the behavior of atom within the magnetic field. It further defines the value of L, that is, it further tells us about the orientation of the angular momentum directions. So it describes the specific orbital within the subshell. To describe an orbital, we need to use all three quantum numbers. So it means that wave functions depends on the three quantum number n, l, m. of r, theta and phi. So the wave function describing the ground state of an hydrogen atom, it can be represented by psi 100 of r theta phi. It is called as the ground state or 1s orbital. So definitely here 100 representing the value of principal quantum number, angular momentum quantum number and magnetic quantum number. So it is the first shell for which n is equal to 1, L will be equal to the 0 and M is equal to 0. So it represents the ground state and 1s orbital. So here we are using the letters instead of numbers to represent the orbitals. So n designates the shell or energy level, and its value is it can be the any integral numbers, that is 1, 2, 3 up to so on. And L designates the subshell, or it tells us about the shape of orbitals. And it can be represented by S, P, D, F. We represent the orbitals subshells by the S, P, D and F. And third quantum number, that is M, magnetic quantum number, it designates the orbital orientation. That is, tells us the orientation of the orbitals within the magnetic field, or it tells us about the specific orbitals. Like if it is the p orbital, then it tells us tells us about its px orbital, which is oriented in the px direction, and then in the py and pz orientation. So it tells us about the specific orbitals. M designates the orbitals orientations. So we can say that when L is equal to 0, when the value of orbital quantum number or angular momentum quantum number is equal to 0, it represents the s orbital. And when the value of L is equal to 1, it represents the p orbital. And if L is equal to 2, then it will be the d orbital, and so on. So when L is equal to 3, it will be the f orbital. So in the same way, for L is equal to 1, for L is equal to 0, we have the s orbital, but when L is equal to 1, then correspondingly the value of magnetic quantum number is the 0. Then it can be the 0 or it can be plus minus 1. So for L is equal to 1, the M has our magnetic quantum number can have the value 0 and plus minus 1. So for L is equal to 1, when M is equal to 0, then it will be the pz orbital. Or when M is equal to plus minus 1, then it will be the px or py orbital. It can be any of the px or py orbital. So here we have another figure in order to summarize the different orbitals, that is for n is equal to 1 for first energy level, for n is equal to 2 second, and for n is equal to 3 represents the third energy level. So it means that when n is equal to 1, then L is equal to 0. It represents the S sub shell, and for this one, value of M or magnetic quantum number is 0. And so for n is equal to 2, when n is equal to 2, value of L can be the 0 and 1. When the value of L is equal to 0, it is s orbital, and correspondingly the magnetic quantum number or M will be equal to the 0. But when L is equal to 1, and that is for p orbital, then the value of magnetic quantum number has 3 possible value, that is plus 1, 0 and minus 1. That is, it's representing the specific orbital, that is px, py and pz orientation of p orbital. In the same way, when principal quantum number n is equal to 3, then value of L can be 0, 1 and 2. When value of L is the 0, then it is s orbital. Correspondingly, the m magnetic quantum number has only one value, that is 0, and when L is equal to 1, it is p orbital, and then correspondingly magnetic quantum number can have the value, three possible value, +1, 0 and -1. And when L is equal to 2 for the d orbital, then the value of magnetic quantum number have the five possible value, that is +2, +1, 0 and -1 and -2. So in the same way we can specify the different orbitals and different specific orbitals, or that is orbitals orientations. We can define all can be defined on the basis of these three quantum numbers. So here we have the table and it representing the different quantum numbers. There are the state levels, wave functions, then orbitals, then hydrogen atom binding energy, and then hydrogen atom binding energy in Joule. So when the quantum number n is equal to 1, L is equal to 0 and m is equal to 0, then this means that the state label will be equal to the 1, 0, 0. That is 1, 0, 0 representing the label of the state. That is, what is the state? What is the state of an electron? So 1, 0, 0 is the state level, and correspondingly for this state the wave function will be 1, 0, 0. And what will be the orbital? Orbital is the 1s orbital. That is, when n is equal to 1, L is equal to 0, m is equal to 0, it represents the 1s orbital. And for correspondingly, its binding energy will be equal to -RH over 1 square, as n is equal to 1, and so its value in Joule will be equal to the minus 2.18 into 10 to the raised power minus 18th of Joule. And now for n is equal to 2, L is equal to 0 and m is equal to 0. So correspondingly the state is 200, and corresponding wave function for this state is psi 200, and definitely it is the 2s state. That is, principal quantum number is 2, L is 0 and m is 0. As we know that when L and m are 0, then it means that it is the s state, as it is the second energy level. N is equal to 2, so it will be the 2s state, and correspondingly its binding energy, that is the second energy shell, so its binding energy is E, and is equal to minus RH over 2 square, and its value will be minus 5.45 into 10 to the raised power minus 18 Joule. And in the same way, when n is equal to 2 and L is equal to 1 and m is equal to 1, and correspondingly the state level is 211 and its wave function is psi 211. Now it means that when n is equal to 2, L is equal to 1. L is equal to 1 means that it is the p state, and m also equal to 1. When m is equal to either +1 or -1, then it means that it can be the either px state or it can be the py state. So correspondingly its binding energy again is the same as for the 200 state, that it is the principal quantum number is same for both of the states, that is minus RH over 2 square is equal to the minus 5.45 into 10 to the raised power minus 18th of Joule. Now we go to when n is equal to 2, L is equal to 1 and m is equal to 0. Now we have another state, that is 2100, and correspondingly wave function is psi 210. So here the principal quantum number is 2, L is equal to 1, representing the p state. When L is equal to 1 and M is equal to 0, M is equal to 0 is specified only for the p z orbital, as we have already discussed in our previous slide that whenever when L is equal to 1 and M is equal to 0, it is specified for the pz orbital, and when, as in the above state, when M is equal to either plus 1 or minus 1, it can be either px state or it can be the py state. So here psi 210, it represents the 2pz orbital. Again, the binding energy is the same because it's the second energy shell representing. So its quantum number, principal quantum number is, again the value of principal quantum number is the 2, and that is minus r h over 2 square, and its value is minus 5.45 into 10 to the raised power minus 18th of joule. Now, at last, when we have n is equal to 2, L is equal to 1, and M is equal to minus 1. So the state level is, that is 2, 1, minus 1, and correspondingly its wave function is psi 2, 1, minus 1. As we know that it is the n where 2 representing the principal quantum number, that is value is 2, and L is equal to 1, it represents the p orbital, and M is equal to, now here M is equal to minus 1. So it means that again it can be either the px orbital or it can be the py orbitals, but it cannot be the pz orbital, because for pz orbital here the value of M should be equal to 0. So again the binding energy is the same because it is the second energy level and principal quantum number is 2. So again it has the same binding energy. So it is only, we have the same binding energy for the S shell and p shells in case of one electron system or for the hydrogen atom. But when we go to the complex system, then the value of S and p orbitals binding energy values will be the different for the complex system. But for the hydrogen atom, we have the same binding energy for the, either it is the s orbital or for the p orbital. So it means that it shows that the hydrogen atom has the different degenerate state. It has the degeneracy. So hydrogen is very important from this point of view, and so we can use the hydrogen atom in different imaging techniques due to its degenerate energy levels. That is, it having the same binding energy for the s and p orbitals. Okay, alright, now we go to the physical interpretation of the wave function. That is how actually the wave function look like and what is the wave function. So it is actually the probability of finding the electron or particular electrons in a defined region, and is proportional to the square of the wave function. So we can define the wave function as wave function amplitude square, that is psi and Lm of r, theta and phi amplitude square, which is equal to the probability density. So that is the density of finding the electron per unit volume, that is wave function depends on the specific r, theta and phi. So there is the specific area, that is per unit area, which has the specific value of the r. specific value of the both of the angles, that is theta and phi. So within that area there will be the probability of finding the electron. So uh, in so the wave functions here, about the wave function, important thing is that we are not only interested in finding the electron around the nucleus, but actually we are interested in finding how the whole electron moves around the nucleus, that is what's the shape of the orbital. So this is the wave function which actually tells us about the shape of the orbitals, that is how electrons moves in a specific volume, in a per unit volume, that is what's the region of finding the probability density, that is these are actually the probabilities, these are the wave functions which have the maximum probability of finding the electron. As here you can see that the wave functions depends on NLM, that are the quantum number, principal quantum number, orbital and magnetic quantum number. Along with this, it depends on the three other things, that is radius and two angles, that are theta and phi. So these all these parameters together define the orbitals. We can define the shape of the orbital. So we can it is the probability of finding the electron per unit volume at specific r, theta and phi. Okay, now there is another way looking at the wave function, that is we can split the wave function as the wave function which depends on r, theta and phi. It depends on the three angles, and along with this it depends on the value of quantum numbers, that is NLM. All these parameters together defines the orbital, shape of the orbital. So we can split this wave function into two parts, that is radial part R and L of R, which is called as the radial part, and Y L M of theta and phi, which is called as the angular part of the wave function. Okay. Okay, alright, if you now look at this pretty good table, here you can see that this one side represents the radial wave function and this one represents the angular wave function. So here for the value of n is equal to 1 and L is equal to 0, we have the radial part of the wave function which depends on the a0, which is the Bohr radius for the hydrogen atom, and z is the atomic number, and so radial wave function for this one is equal to 2 into z over a0 into the raised power 3 by 2 into e power minus z r over a0, and correspondingly for L is equal to 0, whenever n is equal to 1, L is equal to 0, you note that ML is equal to 0, and for the radial part, for L is equal to n is equal to 0 and L is equal to 0, you have this one constant, that is 1 over 4 pi to the power 1 by 2. And when n is equal to 2, for n is equal to 2, again we have the value, two values for the that is the orbital quantum number, or for the angular momentum quantum number, that are the 0 and 1. Again for n is equal to 1 and L is equal to 0, you can see here that this one is the radial part of the wave function for n is equal to 2, and for L is equal to 0, again this will be equal to, again it will be equal to the 1 by 4 pi into 10 to the raised power 1 by 2. But when we go from L is equal to 0 to L is equal to 1, L is equal to 1, here this one represents the radial part of the wave function, and but for L is equal n is equal to 2, L is equal to 1, L is equal to 1, there we have the three different values for the ML along x, y and z direction, that is ML can be either +1, -1, or it can be the 0. So we have three different values for n is equal to 2, L is equal to 1, and ML is equal to 0 plus minus 1. So here you can see that for along the x direction, along y and z direction, we have the value 3 by 4 pi into 10 to the raised power 1 by 2 into sine theta cos phi, and for the y value, for the y direction, it has a value 3 by 4 pi 1 over power 1 by 2 into sine theta sine phi, and for the z direction, it depends only on the cos theta. So it means that when you go to the L is equal to 1, it means that it is the p orbital. Whenever there is the p orbital, you have theta dependence, that is, you have the angular dependence. Now you have the three different values for the angular part of the wave functions. But whenever there is the s orbital, that is whenever n is equal to, either it is n is equal to 1, n is equal to 2, or either it is n is equal to 3. Whenever L is equal to 0, you have s orbital, and for all s orbitals, you have this one constant, and this one is equal to 1 over 4 pi power 1 by 2. So it means that whatever is the principal quantum number, either it is the 1s orbital, it is the 2s orbital, or either it's the 3s, 4s, whatever is the value of s orbitals, so the angular part always remain constant. So it's always equal to 1 over 4 pi 1 over power 1 by 2. So it gives the specific property to the s orbital. It tells you that s orbital only depends on the radial part of the wave function. It has no angular dependence. Here you can see in this equation that there is no angular part. You cannot see any angular dependence. But for the p orbital, here you can see that it depends on the sine theta and sine theta, sine phi, cos theta, and then sine theta, sine phi. So for all three p orbitals, you have the theta and phi dependence. But for the s orbital, here you can see that it only depends. It has no angular dependence. You can see only the constant instead of any angle. So all s orbitals. So it means that this is the constant. This value is constant for all s orbital, and it gives the specific property to the s orbital, and we say that s orbitals are always spherically symmetric. So there will be the equal probability around the nucleus of finding the electron. These are spherically symmetric orbital. Either it is the 1s orbital, it is the 2s or 3s. So it's always spherically symmetric. Now, if you look at the ground state of hydrogen atom, that is 100, it has the wave function of 100 of r, theta and phi, and this means that n is equal to 1, L is equal to 0, and M is equal to 0. So it represents the 1s state of the hydrogen atom. So when we split it into the angular part and radial part, and here you can see that for hydrogen atom Z is equal to 1, and when you put the value of n is equal to Z is equal to 1 for the hydrogen atom, you get your radial wave function will be equal to the 2 e power minus r over a naught into a naught power 3 by 2 into 1 over 4 pi power 1 by 2. So instead of angular part, you have here only this one constant, that is, there is no angular dependence is shown in this equation. So it depends only on the Bohr radius. So this is the for 1s orbital. The same thing happens for the either it is the 2s orbital, or either it's the 3s or 4s orbitals. So the s orbitals will always be spherically symmetrical, and so we have wave function amplitude scale has the probability density of finding the particle is always spherically symmetric. Okay, alright, now we look at the different ways of visualizing the s orbital. So there are the three most common plots which are used to, which are helpers or which are used to visualize an s orbital. The first one is the probability density plot, that is wave function square plot of s orbital, in which the density of the dots represents the probability density. That is, it's here the probability of the dots represents the probability density, means that if the dots are the denser in certain area, or it means that there is the maximum probability of finding the electron, and as compared to those area which are less dense, it means that they have the less dense dotted area, then it means that there is the lower probability of finding the electron. So here the dots represents density of the dot or concentration of the dot in certain area represents the probability density of s orbital. If and so then the next second way of finding the visualizing the probability of s orbital is the wave function plot against r, that is distance from the nucleus. That is, as we have already discussed, we know that the wave, as the wave function s orbitals which are spherically symmetric, it depends only on the distance from the wave functions. It depends only on the distance from the r, from the radius, that is the radial distance from the nucleus. So it's always spherically symmetric. So when by plotting the wave function against the radial distance, we can there is another way of visualizing the s orbital or finding the probability of electron in the s orbital. It depends on the distance from the nucleus. So, and then there is another way of visualizing the s orbital, is that is radial probability density, radial probability distribution as a function of the radius. That is, radial probability density means that as s orbitals are spherically symmetric, it means that there is the radial probability. It means that we can find in s orbital there is always probability finding the electron in a radial probability of finding the electron around the nucleus. So there is radial probability distribution. Whenever we plot the radial probability distribution as a function of radius, that is, again it depends on the distance from the nucleus. So we can further explain the radial probability density distribution, or RPD, that is reports on the probability of finding the electron in a spherical shell. It means that in a spherical shell of thickness dr. So every shell has some thickness. It meant that it has some concentrated areas where there is the maximum probability of finding the electron. So it tells us about the probability of finding the electron in a spherical shell of thickness dr at distance r from the origin. That is, it depends on at some distance from the origin. So the maximum probability or the most probable value of the r is denoted. So this is another, and this is the most important property of the radial probability, that it tells us about the most probable values. That is the most probable value of the r at which there is the maximum probability or wave function amplitude square values. There is the maximum probability of at which we can find the electron. So those value of r, theta and phi, for which we have the maximum probability of finding the electron, it depends on the most probable radius value of r. So here in this plot you can see that this is the radial probability density, radial probability distribution is plotted against the r. So here you can see that this here it is the 0, as it is the nucleus, as so there is the no always there is the 0 probability. It always starts from the 0 because at nucleus we cannot find the electron. So as we go away from the nucleus, then probability start increasing. So at this point there is the maximum probability. This is the most probable radius, maximum probability radius of finding the electron from the nucleus. So for the hydrogen atom, its value is A naught. So A naught we can represent is in the different units, that is the most probable radius for one as hydrogen atom. Its value are can be the 52.9 picometer, or it can be equal to the 0.529 into 10 to raise power minus 10 meter, or it can be the 0.529 angstrom. So here A naught is the Bohr radius. We can express Bohr radius in different units. Okay, now look at this plot. So these are the 1s, 2s and 3s shells, and 3s so these plots represent the wave function amplitude scale wave function scale plots. That is where you can see that for the first 1s orbitals, this is the most concentrated area of 1s orbital. There the density of dot is the larger. So here in the 1s shell it means that there is the maximum probability of finding the electron. So as the it depends when we plot the wave function against the R. This is another way of visualizing the 1s orbital. It means that mm, this we can represent it by this way. And again, when we go to the radial probability distribution against R, so it means that it started from the 0. As we go up, it increases at almost Bohr radius. It has the maximum probability. Most probable radius is equal to the A naught for the 1s orbital, and then it goes to started decreasing. And then at the 2s orbital, here you can see that for 2s orbitals, this one is here is the most concentrated area. This is for the 1s orbitals, and then from 1s orbital then you comes here, then again you have no probability of finding electron. That is, it is the space at area at which there is the value of R. At those value of R, theta and phi, we have the zero probability of finding the electron in this area. So this is the less concentrated, there is the no probability of finding the electron. It means that for those value of R, theta and phi for which wave is wave function scale or probability density is equal to 0, this area, this is called as the node. So we can define the node as the value of R, theta and phi for which the wave function or the wave function scale is equal to 0. So again, from here, when we go further at again at 2s orbital, again we have the maximum probability of finding the electron. So we have here the radial node. As radial node means that as we go away from the distance, it depends on the value of the radial distance. So at 1s there is the maximum probability of finding the electron, and then we have the no probability, zero probability of finding electron. This is called as the node. And again when we reach at the 2s orbitals, again we have the maximum probability of finding the electron. So when we plot it, the wave function against the radial distance, here you can see that from 1s as you go to the this point there is no probability of finding the electron. So this area is represented by the dot. So from here we pass through this area, as that this one is, as we pass through this area and we reach at the 2s. So 2s orbital has the one radial node here. So most of people here think about that this is the this can be the negative probability. So it's not about the probability, it's only about the amplitude of finding the electron. So the amplitude of finding the electron here in this space in the nodal area is always 0. So it's not about the probability. So when we go to the probability distribution plot, radial probability density, we plot the radial probability against R for the 2s orbital. Here you can see that for 1s there is the maximum probability of finding the electron from 1s. As you go to the as you reach here, then again there is the this is the there is the zero concentration area, there is the no dots. So again this is the zero probability of finding the electron. So here you find the radial node. As from this space, you move onward towards the 2s orbitals. As probability started increasing, radial probability started increasing, and then at this point it becomes maximum. So this is the most probable radius for the 2s orbital, and then it again started decreasing. So from 2s to 3s orbital, when you go to the 3s orbital, here you can see that it has the two radial nodes. As we go from 1s to 2s, this area is the radial node, and from 2s again we reach at this area. Again there is the zero probability of finding the electron. These are the value of r, theta and phi, for which the wave function or wave function square has the zero probability. So again here we find a node, and then we started going up into the 3s orbitals, and then as we plot the radial probability distribution against the r, as this is the for 1s, and after 1s you have the radial node, and then for 2s its probability density started increasing, and then it started decreasing, and then you have the again you have another node, and then after passing the nodal area you have the probability density started increasing for the third 3s orbital. So here you have the maximum radial probability density for the 3s orbitals. So here the 3s orbital has the two radial nodes. That is, radial nodes means it depends on the radial distance from the nucleus. So radial nodes, we can define the radial nodes as the value of r for which psi and psi square, that is wave function and wave function amplitude square, is equal to the 0. That is, it depends only on the value of r. In other words, the radial node is the distance from the radius for which there is no probability of finding the electron. That is, at that radial distance at which there is zero probability of finding an electron, that area is called as, at that area the wave function will be equal to the 0, and there will be the no probability of finding the electron, and this area is called as radial node. Okay, now this is another representation of 1s orbital. This is the probability density plot for 1s, and this is the 2s orbital, and this one is the 3s orbitals. Here you can see that in the 1s case there is no node, and for the 2s there is at distance 2a0 you have the one node, and then for the 3s orbital at a distance of 1.9 a0 or 2a0 you have the one node, and again at a distance of 7.1 a0 you have the second node. So a0 here is the Bohr radius. So this is the way of representing the psi. These are the psi amplitude wave scale plots, are the probability density plots for the 1s, 2s and 3s orbitals. So to calculate the number of radial nodes, there is the formula, that is, radial nodes are always equal to the n minus 1 minus L. N is the principal quantum number and L is the orbital or angular momentum quantum number. So here we can calculate the values of the radial node for different orbitals. So first, 1s orbital, for 1s orbital, value of n is equal to 0 and L is also equal to 0. So 1s orbital, 1 minus 0 is equal to 0. So it means that it has 0 radial nodes. And then for 2s orbital, value of n is equal to 2, and then again 1, and again for 2s orbital n is equal to 2, L is equal to 0. So 2 minus 1 minus 0 is equal to 1. It means that 2s orbital has one radial node. Here you can see that here in this is the wave function, that is the probability density plot for the 2s orbitals, and here you can see that it has the one radial node at the position of 2a naught. Okay, and then for 3s orbital, value of n is equal to 0 and L is equal to 0. So it's equal to 3 minus 1 minus 0 is equal to 2. So it has two radial nodes. So here again you can see that this is the probability density plot for the 2s orbital, and 3s orbital, it has the two radial nodes, one at a distance of 1.9 a naught, and there is another radial node that is 7.1 a naught. That is, here is the less probability, zero probability of finding the electron. Here you can see that from here, from this figure, you can visualize that is, there is the maximum probability, there is the zero probability, again there is the maximum concentration of the dot, so there is the maximum probability, and again there is the zero probability of finding the electrons. So for 3s orbitals you have two radial nodes. Okay, for 4p orbitals, for p orbitals, this means that value of n is equal to 4, and for L again 1, and L will be equal to the 1. So for the 4p orbital, 4 minus 1 minus 1 is equal to 2. It means that 4p orbital has two radial nodes. Okay, now we go to the shape of the p orbitals. As we know that the p orbitals, their density not only depends on the radial wave function, it also depends on the value of theta and phi. So its wave function has a radial dependence as well as it has the angular dependence. So as in the last graphs, you have seen that for whenever we go to the from L is equal to 0 to L is equal to 1 into the p orbitals, then for p orbitals we have a different value of ml, that is 0 plus minus 1. So each of one along x, y and z axis, all three p orbitals have different theta and phi dependence as well. So for the p orbitals, unlike s orbitals, the p have theta and phi dependence. So it also depends on the value of angle theta and phi along with the value of r. So the p orbitals are not only spherically symmetric, it also has the angular dependence. So the p orbital consists of two lobes of opposite sign. One is of the positive sign and other one is the negative sign, and these are separated by a nodal plane on which psi or psi amplitude scale is equal to 0. So for the shape of the p orbital, there is the zero probability of finding the p electron in a nodal plane. So whenever there is a nodal plane, there will be the no probability of finding the electrons. So there is, and from the above and below of the nodal planes, you have the two lobes of opposite sign for the p orbital. So thus there is a zero probability of finding the p electron at the nucleus. So there will be the no probability of finding. So there is always, this is well understood, that electrons cannot be within the nucleus. So there is a zero probability of finding the electron at the nucleus. So now look at the shape of p orbitals. Here this one is for the p 2pz orbitals. For 2pz orbitals, here you can see that this one is a nodal plane, that is nodal planes is along xy, that is xy plane is the nodal plane for the pz orbital, and this nodal plane is separating the two lobes of pz orbital. And then when you go to the probability of 2px orbitals, here again this one is the nodal plane that is separating the two lobes of p x orbitals. Here the nodal plane, you can see that it is the yz plane. So the plane, this one is the nodal plane. And then when you go to the py orbitals, again for py orbital, the nodal plane is xy plane. So in the xy plane, there is the nodal plane. For nodal plane, there is the zero probability of finding the electron, or there is the no probability of finding the electron at the nodal plane. So nodal planes are, we can define the nodal planes, the planes that have the no electron density, that is arises from the angular nodes in the wave function. So here, as we have the theta and phi dependence for the p orbital, that is along with the radial distance, it depends on the angular distance, angle theta and phi. P orbital depends on the different angles theta and phi. There are certain orientation for the p orbital, that is pz, px and py orbitals. So their nodal planes are always at certain angle. That is for px z orbitals, here you can see that nodal plane is the xy orientation. For px orbital it has the yz orientation, and for py orbital it has the xz orientation. So there is these nodal planes are also called as the angular nodes, in which the wave function or probability of finding the electron is zero. So we can define the angular nodes. Alright, angular nodes, that is the value for which psi and psi square is 0. That is the wave function or wave function amplitude is 0 at the angular node. So in general, an orbital has n is equal to 1. It represents the total number of the nodes, and n minus 1 total nodes. It has L. L represents L represents the angular node. What is the value of L? So it will be the angular node. And as we have already discussed, that radial nodes can be represented by n minus 1 minus L. So we can try different orbitals and we can define their total nodes, angular nodes and their radial nodes. Now, okay, first let's try the 2s orbital. For 2s orbital, as you know that value of n is equal to 1, and so it has 1 minus 1. It means while n is equal to 2, value of n is equal to 2 for the 2s orbital. So it's 2 minus 1. So it has the 1 total node. Okay, and then for the angular node, that is for 2s orbital, n is equal to 2, L is equal to 0. So it has 0 angular node. And for when you go to the radial node for 2s orbital, so again value of n is equal to 2. So it means that radial nodes are 2 minus 1 minus 0. It has the 1 radial node. No, for a 2p orbital. Okay, for 2p orbital, it means that here the n is equal to 2 and L is equal to it can be either 0 and plus minus 1. So for p orbital, L is 1. For s orbital, L is equal to 0. So for 2p orbital, when n is equal to 2 and L is equal to 0. So total number of nodes will be equal to 2 minus 1, 1 total node, and angular node, for as we know that for p orbital, L is equal to 1, so it has 1 angular node, and radial node, value of n is equal to 2, 2 minus 1 minus 1, so it has the 0 radial node for the 2p orbital. And then 3d orbital, for 3d orbital, n is equal to 3, and for d orbital, value of L, as we have already discussed in our previous slides, that whenever L is equal to 0, it is s orbital. When p is equal to 1 or plus 1 or minus 1, it is the p orbital. And whenever value of L is equal to 2, it has the it will be the d orbital. So for 3d orbital, total number of nodes will be 3 minus 1, 2 total nodes, And angular nodes, for we know that for d orbital value of L is equal to 2, so it has the two angular nodes, and total number of nodes will be 3 minus 1 minus 2. It means it has two radial nodes. Okay, now look at this plot. These plots, here you can see that in these plots it represents the radial probability distribution against distance r for 2s orbital, for 2p orbital, for 3s, 3p and 3d orbital. Here you can see that for the 2s orbitals you have one node as you start from the 0 to, and then you go forward again, there is the zero probability of finding the electron. You have the one node and you go up, there is the maximum radial, most probable radial distance is at between the 5a naught and 10a naught. So for 2s orbital, n is equal to 2 and L is equal to 0. And similarly for the 2p orbital, as you know that n is equal to 2 and L is equal to 1, as we have already discussed that 2p orbital, that for it started from, it said the maximum radial probable radius here, that is between 0 and 5 to 5a naught. So, and in the same way for 3s orbitals, for n is equal to 3 and L is equal to 0, we have two radial node here, for, and there is the maximum probable, most probable radius is between 10a naught and 15a naught. And for 3p orbitals, it has the one radial node as we have already discussed in our previous slide, and its most probable radius is between 10a naught and 15a naught. So in the same way for 3d orbital, most probable radius is at 10a naught. So we have here, we can see the different trends for 2s orbitals. The nodes, radial nodes, have, there is the n minus 1 minus L, that is one radial node. And for 2p orbitals, you have the 2 minus 1 minus 1, it has a 0 radial node. And for 3s orbital, 3 minus 1 minus 0 is equal to 2. You have the two radial nodes, that is this one node and this one node. And for 3p orbital, you have the 3 minus 1 minus 1, you have only one radial node. And in the same way for 3d orbitals, you have the zero radial nodes. As we have already discussed the radial nodes, total nodes and angular node in our previous slide. So you have here the different trends. So as you can see that value of most probable radius, for the 2p is less than for the most probable radius of 2s orbitals. And here you can see that value of most probable radius value of 3d is less than 3p and less than 3s. So it means that value of the most probable radius and started and increasing as you go from 3s. Here you can see that as you go from 3s to 3p to 3d. So this means that 3s is greater than 3p is greater than 3d. So most probable radius for 3s, here you can see that 3s is between 10a naught and 15a naught. And for the 3p, it's here, it's near the 15a naught. And for 3p, it's between 10a naught, 3 naught and 4. Again 3d, here you can see it's at the 10a naught. So the most probable radius value of 3d is less than 3p and less than for 3s. And in the same way you can see the trend in the 2s and 2p orbitals. So as n increases from 1s, as n increases from 1 to 3, the orbital RMP, that is the most probable radius site, increases. So this is the one trend, that is with the value of n. As the value of n increases, the orbital most probable radius size increases. And the second trend you can see in this plot is that as L increases from s orbitals to p and d orbitals, that is, as we go from here, you can see that from s to p to c for a given value of n, as you know that the value of n remain the same as 3p, for it is either is the 3d, 3p or 3s orbital, value of n is the fixed, that is equal to the 3. So for a given value of m, the orbital size, most probable radius size decreases. So as L increases, the most probable radius size decreases, and other trend is as n increases, the most probable radius size increases. So these are the two trends which you can observe from these two plots. Thanks for watching, and for more video please subscribe our channel.